Hi everyone, my name is Dr. Janie Ling-Chin. I am Assistant Professor based in Durham University and a Fellow of Durham Energy Institute. Today I'm going to give a brief presentation on energy content and CO2 emission factor of fuels, energy density, hydrogen production, storage, distribution, and refueling. The figure here shows the energy content and CO2 emission factor of various fuel alternatives. When 1 kilogram of hydrogen is burned, it provides 120 megajoule of energy, which is more than double of the energy provided by other fuel alternatives of the same mass. Potentially, hydrogen has zero carbon emission when it is produced from electrolysis, water splitting, and water thermolysis using energy supplied by a renewable source. When carbon capture, storage, and utilization is integrated with other hydrogen production technologies, such as steam reforming and coal gasification, its carbon emission is low. The table here shows gravimetric and volumetric energy densities and refueling time when energy is stored by diesel, gasoline, hydrogen, and electric battery. Hydrogen can store 5.4 megajoule of energy per kilogram or 3.6 megajoule of energy per liter. Compared to diesel and gasoline, the gravimetric and volumetric energy densities of hydrogen are much lower. However, hydrogen is better than electric battery, which can only store 0.6 megajoule of the energy per kilogram or 1.1 megajoule of energy per liter. In relation to refueling time, hydrogen is comparable to diesel and gasoline. A wide range of hydrogen production technologies has been explored through research and development. They require different feedstocks such as ammonia, biomass, water, and hydrocarbons, including fossil fuels. The energy involved can be biological, electric, photonic, thermal, or chemical. The common forms of hydrogen produced can be categorized as brown, blue, and green. Brown hydrogen is produced from fossil fuels through steam reforming, partial oxidation, coal gasification, etc. Blue hydrogen is hydrogen that has low carbon emission using energy supplied from non-renewable sources where carbon emissions are captured, utilized, or stored. When renewable energy sources are deployed for other hydrogen technologies that have zero carbon emission, such as electrolysis, water splitting, and water thermolysis, the produced hydrogen is green. The figure here shows that steam reforming, coal gasification, alkaline, and proton exchange membrane electrolyzers are mature and have been commercialized. Other hydrogen production technologies are still under development, varying from basic principle to prototype development. Hydrogen storage options can be distinguished as physical and materials-based. Currently, compressed gas and liquid or cryogenic hydrogen are the two commercial ways to store hydrogen. Other alternatives are either in the form of cryo-compressed hydrogen or using storage materials based on physics option, chemistry option, or chemical principles are possible, but not commonly applied yet. In selecting a hydrogen storage option, gravimetric and volumetric energy densities, temperature, and pressure are key parameters to consider. In the first figure, the idea is to be in the top right-hand corner, lightweight and compact. For instance, metaborohydrates, chemical, and cubate-type materials are preferable due to their relatively higher gravimetric and volumetric energy densities. As seen in the second figure, metal hydrate and chemicals are more favorable when the ambient temperature and lower pressures are required. The figure here shows that hydrogen can be distributed from a central production location in a number of ways. They include carbon steel pipelines for hydrogen natural gas blends, fiber reinforced polymer pipelines for gaseous hydrogen, gas tube trailers for compressed hydrogen, container trucks for chemical or metal hydrates, cryo-compressed trailers for cryo-compressed hydrogen, and liquid tankers for liquid hydrogen. There are 4 refueling strategies that may be applied at a station, namely cascade storage, constant pressure, booster compressor, and direct dispensing. The choice is made in line with how hydrogen is distributed and the pressures required. When compressed hydrogen is produced on site, it can be supplied directly to a dispensing unit. To conclude, the hydrogen is clean, has high energy content, can store more energy than electric battery, and its refueling time is comparable to diesel and gasoline. To date, a broad range of technologies has been explored for hydrogen production, storage, and distribution. In terms of production, steam reforming, co-gasification, alkaline, and proton exchange membrane electrolyzers are the commercial technologies applied. Meanwhile, compressed gas and liquid or cryogenic hydrogen are the 2 commercial ways to store hydrogen. Currently, the pipelines, gas tube trailers, and liquid tankers are the options for the distribution for commercialized application. To unlock hydrogen opportunities for more and broad the applications, more research and development is required. With this, I thank you.